Hello everybody. So thanks for being here. Thanks for staying till the last session. Maybe a little bit more technical than the DS one. So, but not too technical. So thanks also to the organizers for inviting me, because I have had a lot of fun preparing the slides, because I'm calling my talk so SWISSto12’s additive manufacturing from early days. And I was really going to the presentations of 2012, 2013, things that were it made me ashamed. Until today, 3D printed based payloads. So I will talk a little bit about Geo. I like the make the Geo great again. So I am Esteban. I'm RF engineer. So my background is on waveguide design. Today in SWISSto12’s, so I joined the company when we were, it was 9 years ago, 3-4 people in the company. So today we are more than 150. So I'm one of the technical guys who remain. So I've been touching everything. I will talk to you about our journey. So our journey goes from 2012 when I discovered SWISSto12’s, or when I applied to a position to work with them. The company was doing TerraRF components. So I will show later the motto, but so we have gone from doing plastic 3D printing in build to print mode of small components for TerraRF applications, which probably never found its industrial application, to today, where we are investing on geo satellites as well, where we are a satellite satellite manufacturer with 4 years under development. So in 10 years, even less than what a geo satellite shall last, we have done quite a change, and 3D printing has been older. The conversation is not only about SWISSto12 3D printing, it's in general about 3D printing. So to tell you a little bit what we have done and what's possible, but also to tell you our experience, and if there is startups today here in the conference. So well, we're still coming and we are advertising one product which we call MCK, but we were in I think in London, probably 2016, we were coming to the Warsaw, and we're a small startup with small booths in UCAP 2015. So till today, where we are a much bigger company. So keep trying, because it pays off eventually. So that's a message to be delivered as well. So it's a journey not about 3D printing, but about people. My CEO told me that it will be a great opportunity to hire people in the conference. So we're still hiring, I should say that. But so SWISSto12’s, it's a lot of people. It's today we are more than between 150 to 200, depending on how you count, if you take the consultants in, the consultants out. But we are a company that in these 10 years has multiplied the size of the company quite a lot. So this will be 50 times. So it's quite a change. It's most of the people are engineers. So guys that could be here, RF engineers, micro engineers, mechanical engineers, antenna engineers, satellite systems engineers. So all these type of profiles, project managers, then operations. And I think what is common in these people. So if you want to go from doing plastic components for academic applications to build satellites, you need to people who likes to push the envelope of what's possible. So I think today SWISSto12 is, for me, a great company, and it's a great company because it has a great team of people. So this will not be possible without them. So the company is today divided in 2 branches, so to speak. So RF products, which we'll do for space, for ground, SATCOM, security, comms, and so on, and satellite. So and what we call HummingSat. I will show a couple of slides. Today, I think we are probably the company. We are not the only ones. Many people are trying with 3D printing, but I think we are the company with probably the widest or broadest heritage in terms of design IP, fabrication IP. And also in terms of heritage, we have more than 1,000 product functions flying in space, and more than 400 ground systems. Ground accounts for airborne, naval, and so on. deliver, including 3D printing components. So 3D printing is a fabrication technology that is here to stay and probably to replace many others. Then we have the satellite side, which we call HummingSat, because it's a small geo, like a hummingbird. And what is this? So the presentation of the idea was quite good, because today we believe that that geo is still having a lot of things to say. So we are trying to develop a small satellite. It's not that small, it's one ton, so it's like 2 kilowatt type of payload. So, and you can see there one of the big birds that SES, Maxar, Loral was doing before. And this will be comparable to maybe Connect BHTS that Didier was showing, and HummingSat. So we are talking about something. Before, when we started, we said dishwasher size, maybe today's 2 dishwashers or a big fridge, but something which is not much bigger than from here to the end of the stand. So the idea is to have and to go and to address the geo market by something which is more agile, not in payload but in execution, something where not to compete with Thales or with Airbus. So when Didier was showing all the cases, it's just to have one case below. So when the operators do not find a business case that close for them to invest on, he has mentioned a 250 million, I will not mention prices, but when this price does not make sense, we want to enable still satellite connectivity. And then government business, so like regional missions and all these type of things is what we are trying to address. Because what he said is right, that the LEO and Kuiper Starlink are disrupting the ecosystem, so you need to come up with different ways to try to survive. So we are doing that, and it's an opportunity to thank ESA, because not only on 3D printing, but also on the satellite. So we have a partnership with them in order for us to develop the satellite to help on the bus. So we have what's called private partnership or private-public partnership project, so a PPP, 3Ps. It's a multinational PPP with, I think, at least 7 countries. These slides are maybe a little bit out of date, but 7 countries that have subscribed. This means that delegations will will contribute to the project, and then we find suppliers in these countries to develop the satellite. So big thanks to ESA. We started with that, and today we have 3 GEOs under development for Inmarsat and 1 GEO under development for Intelsat. I think the official news is that now we have passed CDR, or we have at least closed all the actions, PDR, sorry, for the 2 programs. So I do not recall, I think one is Intelsat is due for 2020, late 2025, and maybe Inmarsat 2026. And there are more GEOs, so when the question of people is, but the GEO market is going down, how are you doing? We are seeing a lot of movement in GEO. So we expect more satellites will follow soon. That's what concerns the HummingSat. So let's talk about 3D printing. I'm not going to say that SWISSto12 is the only company, nor the first company, nor the best company. At least it's the best company for me to work there. But when it comes to 3D printing, we have been there, and I think we have had a significant role in how the space industry has been changing in the way they have been using 3D printing. So here I have some image that you can find in YouTube from OneSat satellites. These are 3D printed feeds, but in what Didier has shown, there were the feeds of Space Inspire, and I have recognized 3D printed feeds. So, and this proves that for the newest products that the companies are going to be developing, 3D printing is going to be there. So in 2015, 2016, so not even 10 years ago, the use of 3D printing was to do brackets. So antenna brackets, lightweight antenna brackets, and that was not even 1% of what you can do with 3D printing. In 2019, we flew our first antenna. In 2022, and between 2019 and 2022, in that time, we have our first major contract with TAS. It was Connect BHTS, where we deliver a bunch of waves. That's public, I can say. So big thanks to Eutelsat and to TAS for that. I think today is still the biggest use of 3D printing in space. So that was a major milestone. today, and this is not us, I have mentioned OneSat, Space Inspired, so the main European primes are using 3D printing for their software-defined radio satellites. We'll see later why, but that's a proof that not only SWISSto12 is going in that direction. And what's interesting is that until 2030 or 2035, if you take all the satellites, I'm not talking about telecoms, but like Earth observation, SAR, defense, electronic warfare, things that will not be like the more friendly applications, but also telecoms. If you take GEOs, LEOs, MEOs, really small satellites, big satellites, and all possible 3D printing approaches like ceramics, plastic, metal, there is more than 17,000 satellites to be developed, and 3D printing is going to have a major role in all those satellites. So for all analog equipment, we can use 3D printing. And that's quite encouraging to build a business plan, to think of trying to be using this application for the future. Because as you will see in the following slides, it is not something, and when we started, and I will show later, we were just trying to produce devices that we were doing before, and we were failing. So you need to learn it and to use it in the way you will be having design rules for all the fabrication techniques. So here we have like a kind of an overview. So first, SWISSto12 are using. There is more fabrication techniques in the like perimeter of 3D printing. We are using metal 3D printing, and it's a technology that goes in a layer by layer way. So you will have a powder bed. You will deposit a layer of powder. You will go with the laser. You will build a layer of your 3D object. You will put another layer of powder. You will do the same, and because of the thickness of the melt pool, so what you see here, so this is the powder. This is the, no, I don't have, sorry. So you have done before a layer of your device. When you are going to do the next one, this is the powder. This is the laser trying to solidify the melt pool, so the thickness of the actual like melting exercise is thicker than the layer of powder, so you are having a micro welding from layer to another layer to another layer, and you build a 3D object. Here we see an example of a waveguide network, how it looks like. So this is the powder and this is the laser. You can see here the laser, how is drawing a layer of this specific component. Why would you use 3D printing? So design flexibility, you can really build anything you want. You can do complex products in a really simple way. So the more complex you make it, you can make a 45 dBi antenna, and it will be probably cheaper to make than making just 50 straight waveguides. Because in the end, there is a component where you are going to, part of the price will be, or the cost will be like related to the amount of material that you are building. So if you use your material to build sophisticated things, you are going to have, rather than to build non-sophisticated things, you are going to have a really good deal for complexity. You can do monolithic, so single piece products, items. That's quite important because you are saving interface, you are saving mass, and when you are saving mass, you are also saving, interface, you are also saving problems like RF leakage, PIM issues, so those things are important, but you are also avoiding assembly, and when you are avoiding assembly, you are saving cost. You are having a quite lightweight, you are only putting material where you need it, so that's quite important. And you are having an excellent repeatability. So whatever you do, either if it works really well, if it's really a disaster, it will be always identical. So that's a really good asset. Then when you are trying to think of constellations or like large production, you can avoid testing. So if you follow the steps, your process is repeatable, and then you are going to obtain all the time the same performance. And we are doing antennas for space that are really S-parameter tested, nothing else. So that's really possible. All these things, in the end, imply that you can do really competitive products. And then, all these are generic. What makes SWISSto12 different is that we were chemically treating the parts that we made, because when everybody says, and even people come to us and they say, oh, but this is very rough, what about the loss? So we are chemically etching all components, and we are plating them. And that's something that Not many others have developed. We have few patents on that, and that's what makes 3D printing go from a tool for rapid prototyping to a tool that you can really use for final applications and for critical missions. So here we have, this is real measurements. So something that you take out of your printer, you test it, maybe you clean it, you depowder it, and then you measure the insertion loss, and then in the end, after having measured thousands of parts, we come to a conductivity that is equivalent to 0.9 dB per meter. But then if we chemically treat it, and if we do all the possible treatments, we will go to 0.4 dB per meter at K band, which is not the ideal copper, but it's pretty acceptable. So a little bit more about us. So this is to explain the process. Today we have we have a workshop which is maybe 5 times smaller than this room, where we can deliver complete space programs, where we have 3D printing machines, all the post fabrication operations, all the machining, all the visual inspection with tomography in order for us to make sure that the interfaces are all correct and so on. A small chemical lab. We have repetition of that in subcontractors, but at least internally we have that. A small chemical lab to do all the chemical treatments, and then facilities for test, environmental, thermal, vibration, and antenna chambers, VNAs, and all this equipment, electronic equipment. So that about SWISSto12. Then, from early days, our early days on this, and I think it was the early days for the complete RF community, to today. So I go back to 2014, 2015, and so the motto of SWISSto12 back then, and indeed SWISSto12, the name, the 212, it's because 10 to the power of 12, because they were doing terahertz equipment, and Swiss is because it was like kind of Swiss machinery, for the watchmaking industry. So that's the origins of the name, because the company was doing terahertz equipment. Those are 2 examples. The motto was SWISSto12 supplies components for high performance terahertz signal transmission. And those were the first things that the company was being famous for. I think they won a prize on a NISA workshop. In this case, I never saw those parts, so I came right when they were advertising those parts. When I came, we had already gone one level lower in terms of terahertz, where 100 Gs was the maximum. But those were the first monolithic waveguides that we were doing in plastic. It was a very cool plastic, like kind of transparent red, that probably would have not supported any environmental application, but it was really cool to see. Also high frequency antennas, like in this case I think it is, if I see well, like also 220, 340 Gs, and things work pretty well. So those were the very earliest, and those are slides that were included in the company presentations that we made back then. Then, in the end, those components worked well, but probably the yield was not something to be proud of. And then we went down, so the company suffered kind of a refocus in terms of markets, and then we went for KU and KE bands. We started to work with ISA at that time. We got our first ARTES-80 project, and this component is what we did before. So people believe, okay, I will do really complex parts, and then I will do in 3D printing, and then everything will be solved. I don't think this part never worked well, because it was not designed for 3D printing. So it was working at that time. When things were working, it was already a success. So we were going to the VNA, like really trying, crossing the fingers. I hope it will work and I will deliver. This was a quite interesting application that I plan to bring back now in metal. 3D printing antenna and reflector antennas with the feed, with the struts, with the sub-reflector. This was, I think, the first collaboration that we really did with ISA, 2015. That was an array where we didn't know too much about arrays. We believe it was a pretty good array, but it had no use. Again, also plastic. But then the plastic, everybody believed that the plastic was great, and we were telling people, oh, plastic is great, but then no one was really buying plastic, so we needed to refocus once again. And these were in 2017 our first metal components. So today we are, and I want to see in 2017 we did our first metal components, which were those simple, stupid waveguides with a twist and a bend, barely working, but working. So in 2017 we did the first, in 2019 we flew our first antenna, and in 2022 we did a first major program. And I think still it took the company 5 years to decide to go for metal, but if we put the T0 for 3D printing in metal till today, or till the first program, I think it's pretty impressive what the team achieved in that time. So it cost me quite a lot to find this slide, this information. It was really hidden on the archives, but these were really the first components we ever did. So, okay, one thing is that you can print, you can metallize, that's great, but then you needed to qualify. So the first program we did, there was not an ECSS standard for 3D printing or for flying 3D printed parts in space. Today there is, and I'm going to use this slide to tell you, I mean, we did our own like MMP qualification, so material and process qualification, in order to demonstrate that technology works and the technology can survive all possible environments. We went to TAS, we went to Airbus, give us the words that you can believe it could happen. We put them together and we did a generic qualification for that. That qualification is what today we need to respect when we are going to do a space program. So we don't have the freedom of being playing with the machine all the time, because otherwise you cannot use it in flight programs. But today here what we can see is examples of when people ask about what is the temperatures you cover. I think here we are having, let me see, probably it's here, when we do the blistering test.
Please be aware that the cloakroom will be closing at 6 p.m. It will not be manned after this. Thank you.
So here we see, for instance, when we have to do thermal cycling, we have tested this technology from minus 180 to plus 170 degrees. We keep it in for it to survive humidity. So we have gone through quite exhaustive material characterization for us to be sure that this can survive in space. Following the qualification of the materials and the techniques and the machines and so on, it goes the product qualification, because you can have a material that works, but if you don't have a design that survives, then so we also have to do that. We did it later. This is an example of a generic qualification that we typically repeat in the products, where you are covering all the mechanical testing, all the thermal testing. Good news is that we don't have to do any more PIM testing, for instance. With the customers, we don't have to do PIM testing, because after a few contracts, they are convinced that this is not going to have any issue, and indeed, we have no issues. We have not have any PIM issue during time, and that's an example of something that will make the prices, the cost in the program more affordable. And then we come to 3D printed-based payloads. So 3D printed-based payloads is, today we are doing antenna feeds from L-band to antenna feeds, filters, waveguide networks, power configuration networks, couplers, everything, all passive equipment. We can do it with 3D printing. All passive waveguide equipment, I would say we can do it with 3D printing, and we can even find ways to do equipment that was not done before in waveguide, to do it in waveguide for the cost that, for instance, PCB components. From L-band to QB band, and flying in some of the most impressive geo programs that has happened. An example, this is some performances. So when people say, okay, but what are the tolerances? In reality, we don't have an answer for tolerances. We really don't know. The tolerances will change from design to design, mechanical design to mechanical design. You can have the same air volume designed for two mechanical engineers, and probably it will not have the same equivalent tolerance in the end. But 3D printing is a process which is a stack-up of tolerances, so depending on how you design, you will have certain tolerances with respect to certain others. But today we can do QB band equipment. We have done quite a lot of flight programs. It's one of the frequency bands where we have more heritage indeed, more in QB than in KU, which is funny. And we can achieve 35 dB cross-pol at 50 gigs. So I think that proves that technology can really deliver what it promises. Then that's I mentioned that the more complex the part is, the better, because you are paying for material that you build. So today we are doing things, and this I go outside space. We are using that to do monolithic antennas with 1,000 radiating elements in KJ band, things that are this big, in one single part, in one single shot. That's where 3D printing becomes interesting. That's an example of when we go for something that had 100 or up to 1,000 parts, if you count all the screws, all the assembly, and all the reworking that it requires, to something that it comes in one shot, that you can really think of mass producing waveguide components, which is a kind of novel concept, but you can really think of doing that. That's an example of like gain antenna, so high gain antenna, 40 dBi for in-flight connectivity. 2030. This is results from a couple of weeks ago. So that's quite good, I would say, because then the feedback from the customers is that mass is 3 times less and price is 2 times less. So then it's a no-brainer if they don't take it. So, and they are taking it. So we are quite happy for that. But those are examples where we are increasing complexity and benefiting from this technology. If you are going to do few antennas like that, okay, but it's still a pretty simple piece of hardware. If you go to really heavy, complicated antennas, this is where 3D printing starts to really bring a lot of value. And then the best in SWISSto12 and the best in 3D printing is always what comes next. And today we are trying to start to combine 3D printing with active components, with solid-state technologies. So we plan to use 3D printing for phase arrays. And that's something that we are probably going to release quite soon. It really works quite well, and we are having phase arrays. So when Didier was asking about all these active arrays in ground, 3D printing is a technology can help deliver the price promises and the performance promises. So my last slide. It has been a quite interesting journey. The journey has not finished. So, and we want to thank all of our customers, first of all, because they are giving us money, but also all of our collaborators because they are helping us. Academic collaborators, there is a lot of academic collaborators that we have worked with, industrial collaborators as well. Sometimes we are asking a lot from them, so thanks to all of them. And thanks for trusting us, and that will be all. So you can see here the journey. So from plastic and not fancy logo and terahertz moto to actual satellite contracts, really leveraging 3D printing.
Okay, thank you very much for the very nice presentation. Do we have questions in the audience? Yes, Anthony, first.
Okay, thank you very much. It was very interesting, and so it's very nice to see a startup that grow that big. My question is quite specific, actually. I was curious about the process you do when you you show the table, the process to
the qualification.
The qualification. I was wondering about one very specific aspect here, not the other one. Yeah, that one. At the beginning, you weight the structure. What is the purpose to do that?
And it's more a matter of control, because the mass at the beginning should be the same, the mass at the end. Mm-hmm. So if something has happened, you are going to also detect it in the mass. But typically the mass is a specification, and the purpose of doing that acceptance is to prove that you have met certain specifications. There is nothing else. Okay. But we keep control, because if, for instance, you have done something and something had got trapped inside, then you are going to notice. And then you know the mass in advance. Sometimes, and I should not say that, so please don't record it, but there is an example of an antenna that should weigh 1.5 kilos and you come in with 2 kilos, and this means that the antenna is full of powder. And in reality, it was the case where the antenna could not be well depowdered, and the powder had solidified, and so it's more to keep control rather than to do everything.
Thank you.
Any other questions? Yes, in the back.
Very, very impressive. And I was wondering, will you be able to go back to the Power 12 at some point?
For today?
To the Power 12 frequency?
So, I mean, you can put 0, 0, 0 to the power of 12, and then in the end you are there. No, so today, I believe we can do up to 100 gigs. Joachim Overhammer was telling me, I think 140 shall be pretty easy. So, okay, maybe not that easy, but I think depending on the component, you can go up to 100 gigs. I believe the typical application 77 or 7186, it's possible. Then you can go. Then you need different machines. You need to adapt the process. You are not going to do the same. So that's a good. It reminds me something. So typically, you don't want to use, if you want to do L band and QV band, you don't want to use. You can use the same machine, but you are not going to use the same process. It will not be the same layer thickness. It will not be the same laser strategy contour and all these things. I'm not the expert there, but so if you want to go to above 100 gigs, other people are doing that. You are going to need different machines and processes that are tailored to that. And provided that you have the right design and the right design approach, the answer is yes. I think to me it's more a concern of how are you going to depowder your piece, because the things are going to be so tiny that you are going to, but the powder is going to also be tiny as well. So I think it shall be possible. Right now we are working with ISA to kind of upgrade the possibilities in terms of what's possible, but we are not targeting yet the 212. So maybe 100 gigs is already a stretch.
Thank you.
Are there any more questions? It's the last occasion where you can ask something at the European Microwave, so please. No? Okay, I have just one very short. You've shown a filter.
Yeah.
Can you comment on how narrowband you can go on filters? Because this one was quite wideband. So
yes, this one, you probably talk about this one.
Yeah.
Yes. So less than 1% for sure.
Okay.
So the thing is that today these examples here were done for 0.5% type of bandwidth. The first, typically you will be, what I also want is to develop filters that do not use tuning screws. Yeah. So you do one shot, and then you measure it and it's a complete disaster. But then you cut it, you start to understand how it works, and you try to, because it's repeatable, you can compensate things out and you can pre-deform and so on. And in that way, you can really reach the less than 0.5% is not a crazy target. You need maybe a few iterations, but yeah, of course, this 0.5% in L band is not the same as in V band. I think KU 0.5%, so 15 gigs or 20 gigs, that's probably feasible and doable. Above, in one program I wanted to use tuning screws because my life will be easier, but the customer didn't want us to use tuning screws because we didn't have experience with them. So we don't have experience with many things, but still we do them. But in that case, we were bleeding quite a bit in order to get it there, but we did it, and it was a 15 gigs, quite narrow band filter with a lot of rejection, transmission zeros, and so on.
Okay, so that's very impressive results. So, are there last call for questions? No? If no, then thank you again. Thank you very much.
Thank you all.